ahora mismo. ¿Vale? Bueno. Okay. So I'm going to introduce Professor Maciej Przanowski before we start. So Professor Przanowski recently retired as professor from the Łódź University of Technology in Poland. He's author of more than 90 papers and advisor or co-advisor of 9 PhD theses in the topics of theoretical physics, mathematical physics, and the theory of relativity. His most important scientific achievements include the proof of the Goldberg-Sachs theorem for the Euclidean signature, obtaining the equation describing a self-dual Einstein space with Euclidean signature with a non-zero cosmological term, which is now called the Przanowski equation, developing the application of quantization deformation in relativity together with Jerzy Plebański, Hugo Compeán, Francisco Turrubiates, and Formansky. This paper has over 150 citations, among other papers. Okay, a long list. He's a reviewer in well-known scientific journals as Mathematical Reviews, Classical and Quantum Gravity, Journal of Physics A, Mathematical and Theoretical, General Relativity and Gravitation, Symmetry, and Acta Physica Polonica B. Professor Przanowski is a member of the Polish Physical Society, and he was also a member of the Sistema Nacional de Investigadores here in Mexico from 2000 to 2004, because he was visitor, an often visitor of the department, of our department. So he's also a member of the American Mathematical Society. He repeatedly visited as a professor at the department of at our department of physics in Simbestav, and for many years he was the closest collaborator of the outstanding Polish physicist and theoretical physicist and a fundamental member of our department, Professor Jerzy Plebański. So thanks, Professor Przanowski, to take our time and to give us this talk. Go ahead.
Okay. So first of all, thanks I would like to thank organizers for inviting me and to give opportunity to give a talk about Plebański's blackboard. In this talk, I would like to tell you about some problems which Plebański wrote on his blackboard, and he in fact left these problems as a heritage to us and to youngest physicists. I take this title from the fact that there exists some blackboard of Richard Feynman. On this blackboard, you can find some problems which Feynman considered as the most important, and also some his sentences on methodology of physics and so on. And Plebański also had such a blackboard, or maybe such blackboards, where he wrote the problems he considered should be solved, and he tried also to solve these problems, but in fact he was not able to find solution in all details. So he left these problems to us, to his students, and to younger physicists. The first problem, which in my opinion was the most important for Jerzy, of course it is individual point of view. everyone remember other problems more interesting or more important. But for me, I think that the most important problem for Plebański was the following, which I can write in the following form. Complex relativity, from complex relativity to real gravitational fields. In my opinion, it was the most important problem for years. To explain this problem, I must explain what is the complex relativity. Complex relativity is theory of four-dimensional complex space-time. The complex space-time is exactly four-dimensional complex manifold endowed with holomorphic metric. So we have holomorphic metric is we can in the following form. Something like that. And this tensor is holomorphic. And we can Plebański knew the following thing, that this metric can be defined by four one-forms, which in spinorial notation can be defined as follows, where A and B, or for A is equal to 1, 2, and B dot is equal to 1 dot B dot, 1 dot 2 dot. Mm-hmm. Mm-hmm. This is four one-forms which define exactly this metric. In the following, this metric, so with the use of these one-forms, metric can be defined as follows. Teraz widać, czy... Mm-hmm. Where we lower and we lower this indices by the use of Levi-Civita symbol, and then this JB defines the following object. Spinorial connection form which is symmetric with respect to A and B. This is one form. Then curvature. This is symmetric spinor with respect to all these indices. Such a spinor, which is also symmetric with respect to AB and symmetric with C dot, D dot, and curvature scalar. This object is spinorial image of self-dual part of Weil conformal tensor, and these two objects define exactly Ricci tensor. And the same GAB dot defines such a connection form. In mathematically, it means that this is a connection form in bundle of dotted spinors. Spinor which defines anti-self-dual part of Weil tensor. And the same two objects. C dot, D dot, and R. Okay. These three objects define exactly curvature. No, pardon. These objects and these define exactly curvature tensor, and these two objects, this curvature, this connection form, and this connection form defines connection, Levi-Civita connection. What is most interesting in complex relativity is that objects GAB and GA dot B dot are independent, and also these objects are independent. So the most or assume that we have vacuum. Vacuum, it means that Ricci tensor is equal to 0. So assume that we have complex vacuum, yes? So assume that R.
Maciej.
Tak, yes?
We have a question from Ricardo. Go ahead, Ricardo.
Okay.
Just a comment. You should use Jersey's terminology. One is heaven, one is hell.
Yes, yes, yes. So if you assume that this is equal to 0, so this is equal to 0, and this is equal to 0, and what happens here in fact, we have two structures. One with this connection and this part of Weil tensor, anti-self-dual part of Weil tensor, and here this connection and self-dual part of Weil tensor. So assume further that this is equal to 0 also, because these objects are independent. So assume that this is also 0. Therefore, you can prove that there exists always such a spinor basis such that gamma A dot B dot is also 0. So all these objects are 0 then. And we are left only with the following thing. And so we have special complex space-time such that this is equal to 0, this also, and this is arbitrary. And here he considered such spaces, and he called these spaces heavenly spaces. The same spaces were considered by Newman in another context, of course, and by Penrose in the context of twistor theory. Twistor called this object, this space, such that this is equal to 0. This space is called by Penrose right flat, right, it means here, right flat heaven. Because we can also consider another case. For example, we assume that this is equal to 0, and then we have this object here, but here, of course, this must be 0. And such a space was called by Jerzy hell, and by Penrose it was called left flat heaven. Left flat, it means that it is 0, so left flat heaven. What the most important result found by Plebański in '75 was that assuming that this is 0, Einstein equations, so Einstein equations for such a space, complex space, then for heaven, can be reduced to one only equation for one function, holomorphic function. And this equation has a very simple form, in fact. It was known in mathematics as Mons-Ampère equation, and it is of the following form. It means derivative. R one. Coordinates are the following. 4 complex coordinates. It doesn't mean that this complex conjugated to this one, no, are independent. And metric is very simple. I write here in Greek. Okay.
Maciek, we stop looking at your video. It's now in this yellow color, rainbow colors.
Yes, because now the current is. We have problems. We have problems with. Okay, wait a minute. We have problems with light.
Okay.
So you cannot see me? No.
No, we just hear you, and the video is in this rainbow bars.
Okay. So it's some problems.
Maybe the camera. I think the camera maybe changed from camera, or the camera disconnected.
No, it's a problem in general in this building with light.
Okay.
Nie wie facet, co zrobić, będzie dzwonił po inżyniera. Także słychać pana, ale to jest dlatego, że jest laptop. A kamera nie pójdzie, bo nie ma prądu. Także może z 5 minut przerwy zróbmy i zobaczymy, czy naprawią, ale jest to mało prawdopodobne.
So the problem with light is.
No tak.
Halo, Jaromirze?
Może otworzymy
Нет,
to.
ну потом все эти как-то теннисисты, ну, может быть, так сказать, там какие-то болезни, но это все-таки не то, что там гребля, там, или футбол, там, когда тебя отбивает бокс, самое, тут все-таки что-то, ну, не знаю, это как-то они тут.
Please be patient because there is no electricity.
Нет, ну, конечно, ничего, да, согласен. Нет,
Let's wait for 5 minutes and we'll see.
All right, we will wait.
Нет, тем более это не за копейки, а там довольно видимо квалифицированные все, так сказать, там много нужно платить. Это не просто так они там. Да.
Tam są uroki tego.
Наверное. Согласен, Солнышко. Так что... Ну да, то есть даже, может быть, ты хочешь сказать, даже самое, может быть, даже в минус уходить, да, какие-то расходы. Ну, хотя нам
Please
накупается.
wait a minute because we have
Уверенно.
with this electricity.
All right.
Ну да, если еще там каких-то родственников с собой захватишь вдруг. Да. Ну да, нет, это точно, если там... Нет, они не будут же в 4 звездочках, так сказать, только 5, это самое понятно, что там. Ну да, нет, ну я согласен. Нет, ну сейчас, видишь, Федераль там не возит с собой там свою семью там и этих. Как-то я сам как-то не обратил на это, то есть, по-моему, там как-то не особо показывали там. Ну да, может, с ковидом связано, может, чуть поменьше, так сказать, будет. Так что это самое... Ладно. Так. Ты смотришь? А у меня тоже. А у меня тоже на экране. Да. 15:30, да. Ну, как ты говоришь, совершенно... Нет, я хочу сказать, сейчас совсем не зря. И раньше это у меня была яркая игра. Даже вот подушка. Но там точно так же не знал. Хотя, кажется, такая... Ну да. Так что это самое... Ну, посмотрим это самое. Нет, ну, эти нормальные, это как будто прям самая такая тяжелейший труд рабский, понимаешь, вот такой не самое...
Vladimir,
Какие-то удары дурацкие, ты стоишь, как сейчас. Ну, вот, так что... Ладно.
So, Maciej,
Yes.
do you think it's possible to use a laptop? Because I see you still have internet. I mean, I think the electricity you need for the camera, right?
Yes.
You don't have light also, lighting.
Exactly. Yes. The camera. Yes, it doesn't work. No?
So, Ricardo, do you have a question for Maciej? Or
Oh, nada más algunos comentarios para llenar mientras se resuelve el problema técnico.
Maciej?
Ajá.
Yeah, okay. Go ahead, Ricardo.
Nada más que yo fue también víctima del pizarrón del profesor Plebański.
Ajá.
Y uno de los problemas que me pareció el más cercano a su corazón eran soluciones exactas de tipo N con twist.
Yes, está.
No
Sí,
sé si lo ibas a comentar en el procedimiento. Y la otra cosa es que en su formulación de la gravedad en términos de dos formas, resolvió el problema de la realidad con un producto de dos formas. Él la llamaba sigma. Sigma celestiales, wedge sigma infernales.
Infernales.
Y se ha trabajado mucho en esto en los últimos años.
Ajá.
Entonces, de alguna manera, creo que uno de sus deseos, no sé si se ha cumplido por completo, pero se ha hecho mucho trabajo. por su relevancia en loop quantum gravity.
No, pero el problema es que no se sabe, el problema principal es cómo obtener, por ejemplo, tienes solución que o tienes métrica compleja. ¿Cómo obtener de métrica compleja métrica con signatura lorentziana? ¿Cómo obtener esto? Este es el problema.
Irreal.
Sí, se puede. Sí. ¿Cómo hacer una superposición de de objetos infernos con
we
objetos.
can speak English, Maciej.
Okay. How to make superposition of hellish objects and heavenly objects to obtain solution with Lorentz signature. This is problem. How to construct. Yes. How to construct.
Sorry, just to understand. So there are two problems. One, I want real solutions because we live in a real world. Two, I want a Lorentzian signature.
Yes.
Okay.
This is the main problem. But he believes that it's possible, and so he made this superposition by some superposition of tetrads. He made the following thing, that you have one tetrad which gives you heavenly space. If you change orientation, you have hellish space. And then you make some superposition of these two tetrads to obtain solution with Lorentzian signature. But what you have really, so you have one solution with one tetrad. You have four complex coordinates, so 8 real coordinates. So in fact, this space is eight dimensional, and you must find some four-dimensional submanifold of this 8-dimensional space. And it is very difficult. And you must also obtain some Lorentzian metric on this 4-dimensional submanifold. And it is very difficult problem. And this is very difficult problem because you don't know how to do it, because the main problem is that Einstein equations are nonlinear.
Of course.
And so there is some mixture of real and imaginary parts of metric if you make complexification. Because idea to obtain real solutions from complex solutions goes to paper by Trautmann in '62. it was very nice, really nice paper where Trautmann showed how to find Maxwell's, or more general, how to find solutions, real solutions to linear equations which are covariant with respect to Lorentz transformation. His idea was the following: take for example, Maxwell equations. Take Maxwell equations, then complexify these equations. You have complex Maxwell equations. Take some solution and make Lorentz, but complex Lorentz transformation. Then take real part and complex part of the solution, and because Maxwell equation
Maxwell equations are linear. What I think we lost Maciej, David.
Yes. We stop hearing after Maxwell equations.
Yeah.
But
I don't know. I was just trying to fill the void.
it's okay, because I had the same question actually, like about the motivation that
the question that I think Jersey was after is we do understand linearized gravity, but he wanted exact solution to non-linear gravitons, sort of a non-perturbative approach. And he made progress in that direction. Going back to Maxwell equation, you should be familiar with Plebański's work that is relevant to transformation optics, where he put the Maxwell equation in a curved background.
yes, for sure. This I know, these equations in space.
You probably know them in detail.
Yes. So I'm gonna, I don't know what we should do. I'm gonna send an email to Maciej just to let him know what he thinks we should do.
Oops. Pardon.
Hi Maciej, we see your signal back. But you have your microphone off.
Niech pan teraz spróbuje, czy będzie słychać pan chociaż.
Can you hear me?
Yes.
Can you hear me? Okay. But you don't see, you cannot see. You see me?
No. Not yet.
Maćku,
No.
nie widać nic, Maćku.
Wiesz co, słuchaj, no wysiadła, wyobraź sobie, bo wysiadła w całym budynku elektryczność fizyki. Macabra.
Dicen que hay corte de electricidad en todo el edificio.
Tak, en todo el edificio. De física y no saben qué hacer.
Eso es un desastre, simplemente.
Well, don't worry, Maciek. These things happen. You don't have control on this. So,
I Maćku, a jak wy się łączycie z internetem? Skąd macie internet?
No właśnie, nie wiem, teraz jakoś się połączył z internetem. W tym momencie, bo w ogóle zgasł cały internet, wiesz? Internet wysiadł, ale przez telefon, wiesz?
Aha.
okay.
I przez telefon i przez laptopa, tak?
Przez laptopa i przez telefon, tak.
A nie możecie włączyć kamery w laptopie?
Łączymy kamerę.
Tak, próbuję włączyć. Tak.
Ellos intentan conectar la cámara de laptop.
Okay.
All right.
Y el internet ellos tienen por teléfono celular.
We see you now.
O!
On the laptop, Maciek.
Widzimy cię, Maćku.
Dobra.
Więc, ale już na tablicy to raczej to już może pan najwyżej na siedząco po prostu.
Okej.
Bo już na tablicy nie obejmiemy.
Widzimy ciebie, widzimy, Maćku. Możesz kontynuować.
Ale tablicy nie oczywiście. Tablicy nie widzicie.
Widzimy kawałek. Gdyby komputer leciutko przesunąć w lewo twoje, to wtedy byłaby i tablica widoczna.
No widzisz teraz?
No widzimy, ale marnie te tablice widzimy. Teraz lepiej widać. David, ¿puedes poner la pantalla de Maciek? Ahora la pantalla completa para mí, porque yo veo solamente en
I already did it with the spotlight, but I think it's not working for everyone. I see also Vladimir. Vladimir, do you hear me? Can you turn your camera off?
Vladimir nie słyszy.
If not, what everyone should do, I don't know why it's not working, the spotlight, but what everyone can do is just to click on the three dots and put pin on Maciek's video feed. Para que todos vean en pantalla completa, digamos, a Maciek, le pueden dar en los tres puntitos, en las opciones y ponerle pin. Y entonces ya lo ven solamente a él, digamos, o mayoritariamente a él. Se supone que esa opción debería funcionar si yo lo marco con Spotlight, pero no está funcionando. No sé por qué. Vamos a ver.
A mí sí me aparece en primer plano.
Bueno, muy bien. Entonces, podemos continuar. So, Maciek, we see 3/4. Can you move a bit more to the left, your laptop?
Okay.
Yeah. Yeah, that's it. We see all the lower backward.
Okay.
¿Está bien?
Yes.
Znakomicie.
Okay.
Muy bien, se ve muy bien.
So okay. Entonces puedo continuar.
Yes.
Okay. So Plebański's question was how to obtain, because we have the following situation. 10 Einstein equations can be reduced to one only equation for one function. And metric is defined by this one function, a second derivative. So Plebański asks how to obtain from this metric, how to obtain real metric, real gravitational field with real gravitational field. The problem is that for real gravitational field, these two objects are not independent. So complex conjugated of CABCD is equal to exactly this. So if this element is equal to 0, this is also 0. And so the space is flat, in fact. So it is also, yes?
Can you lower a bit your camera, because we don't see the lower part of the blackboard? Yeah, that's enough. Yes.
Oh.
Thank you.
We have this?
Yes, we see it. Yeah.
Okay, so if this is 0, this is also 0. So the space is flat and is trivial. So Plebański thought of the following procedure. Find Heavenly space and then change orientation, so you have hellish space, and make some superposition of these two things. How make this superposition? It is, of course, open problem. It was done, for example, in some papers by Plebański, Hugo Compean, Alberto Garcia, also by Plebański and me and my student Formański, and for example, also the problem was considered by David Robinson also, but the general method is not known. Until now, is not known. How to make this superposition? Because from mathematical point of view, we have four-dimensional complex space with holomorphic metric, and we must. So if we have four-dimensional complex space, so it means that it's eight-dimensional real space, and we must find some four-dimensional submanifold which has appropriate metric. So the metric with Lorentzian signature. So with signature this. And this is, so the problem is still open, and I would like to encourage young students of physics to consider this, to find. So problem we can following put following problem. Find the method of superposition of heavenly space and hellish space to obtain real solution of Einstein equations too. It is not, from physical point of view, it seems to be very clear, because heavenly space is from the point of view of Penrose, from his twistor theory, heavenly space is graviton, is nonlinear graviton. So right flat heavenly space. So when we have this equals to 0, so we have right flat heaven is in twistor theory of Penrose. Such an object is nonlinear graviton with helicity 2. And left flat heaven, so when this is 0, is graviton with helicity -2. And so superposition of these two objects is nothing else but superposition of gravitons with helicity +2 and -2. So physically, it seems to be resonant to find real metric from such a superposition. But as I said, nobody knows how to find some theory of such of superpositions of these two objects. We have only some examples of this, but nobody knows how to make this in general. Plebański thinking about this problem, he published with Ivor Robinson, published a paper in '76, where he found some generalization of this equation, of heavenly equation. In this paper, they assume that this is not 0. We have vacuum, complex vacuum, so Ricci tensor is equal to 0, but this is not 0, but is of minimal degeneration. What it means? It means the following. Because this spinor and this also are symmetric, totally symmetric, so there exists some theorem by Penrose that it can be right in the following form in general. This parenthesis means symmetrization. So, this theorem by Penrose says that there exist such spinors, K, L, M, N, that CA dot B dot C dot is equal to this thing. And degeneration means that at least two of these spinors are overlap. So we have the following thing. It means this is minimal degeneration, algebraic degeneration. And David, can you hear me still or no?
Yes, yes.
Yes, okay. And you can see all these things? Oh, yes.
Yes, we only see the lower blackboard, but we do.
Yes, okay.
Yeah.
And so in this paper by Plebański and Robinson, it is assumed that C, A dot, B dot, C dot, no is zero. It's not zero, but is with minimal degeneration. And what is fantastic, they managed to reduce 10 Einstein equations in vacuum, complex Einstein equations, to one only equation, which is called now hyperheavenly equation, because such a space where C A dot B dot C dot is has minimal degeneration is called by them hyperheavenly space. So when this is equal to zero, so we have heavenly space, and when it is not zero but is degenerated, algebraically degenerated, is hyperheavenly space. And also for such a space, one can reduce Einstein equations to one only equation. For one function, this equation is nonlinear of second order. And this result motivated Plebański to formulate further program, his program. A program was very simple. Consider heavenly space, consider space, but not heavenly space, but space such that CAB, CD, complex space, of course, CABCD is of some type, okay? So has some, because CABCD is also of the following form. Assume that CABCD is of some type, for example, of this type. And is of the same time. So this. Of course, these spinors are independent. So we have the same time here and the same time here, the same type here. Why? Because if you look for real Lorentzian space, so for Lorentzian space, you have the following thing. So type of this spinor is exactly the same as type of this spinor. So you should assume that type of this spinor in complex space is the same as type of this spinor. And then solve. Idea is you must solve hyperheavenly equation. So you find such a solution that this type is the same as this type. When you find this, you have you can look for Lorentz for what is called real slice. So you can look for some submanifold, four-dimensional submanifold, which has metric of this this Lorentzian signature. And so the program is very clear, but to obtain from holomorphic metric, real metric, by making real slice is also difficult. There is no theory on general theory which can enable us such a procedure. But there are some results on this. So one can find some examples of this situation. And for example, it was found by for example, my colleague Adam Chudecki found real slices of the types 2, so of this minimal degeneration. This is type 2 in Penrose classification. So with such a case, he obtained and for type D means that we have here the same spinors. This is type T according to Penrose classification. So he was able to find real slices for such cases, and also real slices for example, type N of the type Trautmann-Robinson, also, and type N of the Kund type, solution of the Kund type. But still, we have no theory of general procedure. How to obtain from having solution of hyperheavenly equation, how to find real slice of Lorentzian signature. But this problem is still must be solved because it's still open. This problem, apparently, this problem is outside the mainstream of interest in physics, but it is not so, because it is very interesting that we find unexpectedly the same problems in many branches of physics. So I can show you the following thing. If you assume that metric is not Lorentzian, but has signature or Euclidean signature, so has the following signature. And we consider gravitational field, and we consider Einstein equation. So solution for such a signature is known in physics as gravitational instanton, and it plays an important role in quantum gravity, in the form of, for example, in Feynman integrals or sum in gravitational theory. And what can be shown very easily? It can be shown because for such a signature, while spinor, undotted while spinor, and dotted while spinor are independent. So we can consider heavenly space exactly in this case, in the case of real metric is such a signature. And we arrive at exactly at the same equation as heavenly equation. But now, metric is of course as in the complex case, second derivative of some scalar, but this scalar is real function of coordinates such that now Z1 bar is complex conjugated to this. So we have four-dimensional space with metric of this signature. Only one equation, Monge-Ampère equation. Metric is defined in the following form. And so this space is self-dual. It means that and also of course, mathematicians know very well such a space, because this is exactly the color space. This is color potential in mathematics. If it's compact, so we have Calabi-Yau spaces. But we can do more. We can assume that there is zero, but we can assume the following thing, that but there exists lambda, so cosmological term and so this equation, so space is not color, but this equation is modified. And we have also metric is defined by such a function, but this function satisfies the following equation. Not very difficult. One bar So if we have this, if we assume that there exists that it is in general Einstein space, not with lambda equal to 0, but general Einstein space, so equation is the following. Metric I don't write, but metric is also defined by this scalar. And this equation also appears in many problems. For example, in twistor string theory, the last paper from this year by Mason and others, where he showed this equation appears in twistor string theory. And also, there are also other possibilities to. In fact, I don't write it, but in fact we can. But in fact we can find for all degenerated cases we can reduce Einstein equations to one only equation for one function. And so it is one point. Other point is very interesting also. When we assume that space, or four-dimensional space, is
Czyli może pan znowu używać tabli.
tak? You can see me, okay?
Yeah.
It's okay.
Yeah.
Because,
Now,
but I have time or I haven't any.
you have time still. Like.
Huh?
Yes, you have time. Yeah, continue, please.
Okay, thanks. Because now electricity is okay, so.
I see. Yeah. We now we can see both blackboards at the same time.
Okay, yes. Another case very interesting, but rather in mathematics maybe, is when signature is the following. So it occurs, it was rather unexpected that hyperheavenly space, but real version of hyperheavenly space. So we assume that in this case is real. This spinor is real, and this spinor is also real. And so we can repeat all machinery of Plebański and Robinson to obtain hyperheavenly equation. And we can, in this case, we arrive at the same hyperheavenly equation, but metric is real. Metric is real from the very beginning, but signature is this. So if our word has two times, so it's okay, but our word has only one time, so it's not okay for us, but from mathematical point of view, it is very interesting that indeed for real metric of such a signature, we can reduce Einstein equations to one equation for one's real function. And this equation is of the second order. And it can be done without any symmetry. So it's very, very difficult, very, very strange, I think. That we don't assume any symmetry, but Einstein equation can be reduced to one only equation. I don't write, because I don't write this equation. Hyperheavenly equation with real coordinates. And we can obtain from this one equation, we can obtain metric also, having one only function. But the crucial point of in reduction of Einstein equations to one equation, to one hyperheavenly equation, lies in the following thing: in existence of two-dimensional totally null surfaces in the space. When Plebański and Robinson reduced Einstein equations to one equation, hyperheavenly equation, they used very nice and very, very strong theorem proved by Plebański and Hassian in 1975. This theorem is some generalization of Goldberg-Sachs theorem known in general relativity, and theorem by Plebański and Hassian says the following thing, that if complex space-time is satisfies this equation, complex space-time. So I come back to complex space-time, as I assume that this space is vacuum. So we have vacuum Einstein equations, complex Einstein equations. So this spinor is algebraically degenerated, so at least is of the following form. This is symmetrization, at least of the following form. So two of these spinors are the same, exactly. Then, so if we have this and this, so there exists congruence, or in mathematical language is foliation, congruence of two-dimensional surfaces, totally null, totally geodesic. So this space can be it's only diagram, of course. This space can be foliated by two-dimensional, totally null, totally geodesic. It means that null geodesic lies here. They are constructed from null geodesic. And inversely, if this is the case, and this is the case, so it must be degenerated space. It was the main point where Plebański and Robinson were able to reduce Einstein equations to one equation, because they could choose some appropriate null tetrad with this, when we have such a foliation. So we can say that this is the most important thing. In fact, this foliation is the most important thing. So we can generalize hyperheavenly spaces and define what Plebański also did, is weak hyperheavenly spaces. By weak hyperheavenly spaces, we mean spaces which don't satisfy this, but can be foliated with null surfaces. These surfaces are called null strings, by null strings, so can be foliated by null strings, and CABCD is degenerated. So weak heavens are C. CABCD, or of course, Condot here, one of them. So, of course, heavenly space is weak heaven, but weak heaven, because this can be not equal to 0, so it's not of course, heavenly space, but we know, Plebański showed, how general metric looks for such a space, for weak heavenly space. And for weak heavenly space, Plebański and Robinson showed that for weak heavenly space, the metric can be, in general, described in the following form. Here we have a holomorphic function. Here is square. Here is symmetrization. Here you have symmetric stereo. So we have only 3 functions here. Of course, it's sum over A dot, B dot. Coordinates are phi square can be are 2 possibilities. Phi is equal to 1. Can be put to 1, or can be or not. So cannot put 1 is depends on P A dot. So in general, phi is a function of P A dot, or is equal to, or we can put to 1. In the case when this phi is equal to 1, this is, so assume that phi is equal to 1. Such a space is called by Plebański and Robinson non-expanding hyperheavenly space. This non-expanding means exactly that these null strings are parallelly propagated. Are parallel. So for phi equal to 1, they are parallelly propagated. What is very interesting, we can, the same situation can be found in the case when we have metric of this signature.
Maciej,
Yes?
we have a question.
Yes, of course.
Eric, go ahead.
Hi. Sorry, is this Einstein space?
Perdón?
Is an Einstein space? ¿Es un espacio de Einstein? ¿Satisface las ecuaciones de Einstein?
No, this space, exactly.
Yes.
This?
Yes.
No, this space is known now in mathematics as Walker space.
Okay.
This is Walker space. In 50, Walker defined the following spaces, which are now called Walker spaces, and Walker space is a triple where we have, this is differential manifold, but with metric, but with indefinite metric. This is Riemannian space, pseudo-Riemannian space. This is metric and dimensional, because Walker defined this in general. For general n, ds squared, and d, where d is r-dimensional where these are dimensional parallel or parallelly propagated distribution on Mn. Distribution it means I have some vectors, and each point I have some r-dimensional subspace of tangent space, and these subspaces are parallelly propagated. One can prove, okay, and Walker considered these spaces, and in four dimensional space, if we assume, so assuming that r is equal to 2, so we have four-dimensional space with signature indefinite, but with such, with metric of this signature, and we have r equal to 2, So this distribution are two-dimensional. So it occurs exactly that this is that metric must be of the following form of this worker space. So the worker space is in fact exactly in four-dimensional space of this signature, and with r equal to 2, worker space is exactly heavenly space, non-expanding heavenly space. So we can use all the machinery of heavenly spaces to investigate worker spaces. And so we were able to, with Adam Hudecki, to find, for example, self-dual worker spaces and metrics of self-dual worker spaces, and so on. Of course, it was also in 93, another spaces were considered, so-called Osserman spaces, and now we know that these spaces are exactly heavenly spaces with lambda. And with this signature, we can consider these Osserman spaces also from the point of view of heavenly spaces, now heavenly spaces, of course, and we can prove that conjecture by Osserman is not true in general. This conjecture was stated in 1990, and it says that Osserman spaces are global Osserman spaces are the spaces are symmetric of the first rank, and we show that it's not true because we have found solution of hyperheavenly equation which gives metric explicitly, and we can show very easily that such a metric is not symmetric. So this conjecture is not true in general. Okay, so it's only part of talk I wanted to give, because I wanted to tell you also about what Ricardo says about type n with twist. When Plebański tried to solve this equation for type n with twist. Type n, it means that CABCD is of the following form. And Plebański wanted to solve Einstein equations for this case, but assuming also that null geodesic defined by this spinor in our space-time is twisted, so makes some rotation. We know only one solution. Up until now, we know only one solution of this type. This solution is Hauser solution, known from since 1974. And Plebański looked for new solutions, and he paid a high price for this, because he tireless and and he suffered from grave stroke, and this stroke marked him for the rest of his life. But it is also a problem which could be solved, and I encourage also the young physicists to look for solutions. And another, this is the last sentence I would like to say, is the last problem which Plebański also showed me was the problem of quantum mechanics in phase space. How to formulate quantum mechanics in the form of classical mechanics, so on phase space. It is a very interesting problem. Because this problem shows that also problem which is seems to be purely quantum problem from quantum physics, but it has very interesting application also is in gravitation, in for example, non-commutative geometry, also in quantum gravity. Now we know how to generalize this formulation for discrete observables, such as spin. So we can define quantum mechanics on phase space also for the particle with spin, for example. It was also the problem by Plebański. That Plebański was gave the lectures in Warsaw in '68 maybe, and he has notes from this lecture titled Poisson brackets and commutators. By the way, classes for these lectures had Piotr Kielanowski, and these lectures he also showed to Sternheimer. So Sternheimer wrote about that Plebański showed him these lectures, and then in '75 and in '78 the famous paper by Sternheimer, by Bayen, Flatot, Sternheimer, Fronsdal, and Lichnerowicz about deformation quantization appeared. So this is what I would like to say. Thank you very much.
Thank you, Maciej, for your talk.
Sorry for this light, but
don't worry. Technical problems, we know about that.
Yes. So yes, this is theoretical physics, and when we speak about theoretical physics, so technical problems are always
always part. So now we have some time for questions. If you want to ask a question to Professor Maciej, please use the raise hand, and I will give you the word. So maybe I will start with the first question, so they have time to think about. Somebody else has time to think about another question. So you told us about this hyper-heavenly equation that it's equivalent to the 10 Einstein field equations in a single equation. So
Yes.
in the Einstein equation, the main quantities are the Einstein tensor, which is like a space-time geometry, and then the stress energy tensor. So can you tell us what are the equivalent quantities in this hyper heavenly equation?
Equivalent? No. Only you must take only vacuum equations. So you have no tensor here of energy or something like that. And yes, and if you assume that this thing is degenerated, you have this foliation, and this foliation gives you that metric is of the following form. And then you have only this function to obtain, and you write Einstein equations and find some appropriate coordinates, nothing else. Nothing else. It's only some looking for new coordinates which will give you such a reduction.
All right. Yes, I see it now.
So this existence of this foliation is such a strong assumption that you can make this. It is mystery of geometry.
Okay. So we have another questions. Eloy, go ahead.
Okay. Maciej, thanks for your talk, for your nice talk, which is a window to the head of Plebański, which is a privilege. Another topic in which Plebański was also a champion was in nonlinear electrodynamics.
Yes, yes.
I remember a very nice paper of Salazar, Garcia, and Plebański,
yes,
where they have a very nice paragraph at the end when they say that finding rotating solution for nonlinear electrodynamics was one of the most important challenges in the world theory of exact solutions. Recently, nonlinear electrodynamics has become very popular by many reasons, but one of the reasons is also the fact that they are very nice sources for regular black holes with Hopf singularity.
Yes.
But this paragraph of this paper of the paper of Salazar Garcia and Plebański is very important right now because nobody knows a rotating regeneration of these black holes which are sourced by nonlinear electrodynamics.
Yes.
Can you comment a little about this problem, because it was also one of the open problems that Plebański thought that was very important.
Yes, you see, I was interested in but not in this problem. I was interested. I know this paper by Salazar and Garcia and Plebański. It is really very nice, very nice paper. But the problem there was mainly to consider duality rotation in
exactly.
Duality rotation in this, and not so I was interested in this problem, how to define duality rotation in nonlinear electrodynamics. And so I don't know how because I'm not interested. I was not interested in the problem of nonlinear electrodynamic source in gravitation. So I don't know how this problem states now. I don't know.
No, the problem remains open. My question was more in the sense of if you remember something of Plebański in the last years, related with this problem. Do you remember some discussion
I
about
know.
that, or some words of him about that?
Yes, yes, but you know, yeah, because I was not in there, so I consider only these problems which was connected with exactly with this complex relativity. So I don't know how it stands now. This problem
Okay.
is. I know that of course nonlinear electrodynamics now is very popular and is. But I don't know what are the solutions now.
Okay. Thanks, Maciej. Thanks
Thanks.
for your talk.
Thanks, Eloy, for your question. We have another question from Alberto Garcia.
Thank you, Maciej. This is Alberto. Okay, I don't know really if there was some progress in the problem in that in the case of heavenly hell with electromagnetism. I recall that I participate in that piece, and we contribute with something. Perhaps some work were so good.
Yes, I remember. Yes, I remember this work when you with Jerzy. Yes, with Jerzy you found this complexification of type D solution. Yes, I remember this very well. It was very interesting. And for example, I know new results are here because some general solution of type D was found by my colleague, and I must say you, it was with exactly with the tensor of matter, complex matter of electromagnetic type. Yes, some new solutions have been found by Hudecki. I don't have here this, but yes, they were found.
Okay. I work with Jerzy and Fred Ernst in the complexification of this, to say, Ernst equation in the complex space, and we got some result about this complex Ernst potential and real complex, and how to make a coincidence of them. This was a point to get some real a slice of these solutions. But we didn't publish that paper. Well, that works. There were no paper. At least I will have a call to give a call in the future, so I shall remember perhaps about this point, and also your contribution on this aspect. Okay, thank you.
Thanks, Alberto. Thanks.
Oh, yeah.
Thanks, Alberto, for your question. I don't see any other questions. If there is, please just talk now. Otherwise, maybe Maciej, can I ask you one last question?
Okay.
Maybe you can help us. Wait. There's more questions by Ricardo Capovilla. Go ahead, Ricardo.
Just a comment about Jerzy Plebański's blackboard. When I arrived in Mexico, thanks to him, I was in his office, and he had trouble writing, so he would put a question, dictate a question from his wonderful notes,
Yes.
which is something else I learned from the master. And I would write the question on the blackboard. And I was coming from a different culture, so I would ask him why the question, what's the motivation? And his answer was, because it's on the blackboard. Probably Alberto remembers something similar.
Yeah, sure.
Just an anecdote. Thanks for your talk.
Thanks.
Life difficulties.
Thanks, Ricardo. We have another participation from Vladimir.
Hola, Vladimir.
Oh, yes.
Hola.
First of all, Maciej, I would like to say you hello.
Hello.
Yes,
Hello.
and, to say that you look fine, beautiful. Yes.
You too. You too.
No, but you reduced the heritage of Jersey to complex relativity. But I would like to ask you, probably you can say something, a few words about the exact solutions. What were the goals of Plebański or Jersey in the area of exact solutions? I don't know what he wanted to do and what he left to do for us and for younger investigators, researchers.
Yes, he wanted, first of all, he wanted to solve type N. You know, it was the problem for his life, to solve N with twist, problem to solve vacuum equation with twist, vacuum, because some solution with lambda is known, but he wanted to solve with the solution in vacuum. It was the first thing, because and then the next problem was to solve general Petrov type 1. So when we have no degeneration of Weil tensor.
Okay.
To the most general case, and he used here his new method of separation of Einsteinian structures. Ricardo said about this thing, because Ricardo worked on this problem also to use this separation to find solution of Einstein equation. New method of Plebański wanted to find new methods of solving Einstein equations, and this method was not by Cartan equation, but by second form, with the use of second form. It was exactly what Ricardo was also working on.
Okay.
So it was the second problem, and the third one, yes, the general type, Petrov type, and the case of type N.
Okay, thank you, Maciej. So,
thanks, Vladimir.
So, thank you all for your questions. I think we finished the questions. So, if you can you open your microphones and cameras so we can thank Professor Maciej for his talk today.
Thanks.
It's very late. time, and we managed to overcome these technical difficulties. And I thank you for your talk.
Thanks. Thanks.
So thanks also to
one
everyone
last
that
comment. I'm very envious of your blackboards.
Yes.
Magic blackboards.
Thanks.
We need blackboard like this in the Athens.
Yeah.
I hope the chief of the department is here and hear that.
He's not here, but we should tell him. All right. Thanks everyone for coming. So next week we have David Fernandez talk. I will send you later today the email. So last week we have some problem with the email. I don't know what was exactly, but I hope it will work out this week. Okay. See you next week.
See
Bye.
you.
Ciao.
Bye. Thanks everyone. Bye. Bye.